definitely talk about again. I want to make sure that even the stuff kind of leading up to that made sense as well. So let's do a quick recap and make sure that we're feeling okay, answer some questions, and then we can kind of build from there. So basically, main ideas from yesterday, we're trying to get comfortable with the relationships that we see. Actually, let me back up even. Between a function and its derivative. And just kind of trying to make those kind of simple connections. And we kind of just made our own little table here at the top of page 124, where we looked back at this graph and kind of got a sense for what happens when we take a look at the slope of the tangent line kind of moving along a function from left to right. And we're always going to view things in that order from left to right. It just makes it really easy to read that way, and it kind of makes sense in our brains to like imagine moving along that path. And however you want to envision that, I think is up to you. Some of the analogies that I came up with that I use a lot is, we're just kind of like rolling a ball up and down the hill, or riding a roller coaster that looks like that from the side, or we're hiking up and down a mountain and we're just kind of looking at our elevation changes from that side, trying to make connections between what the derivative value actually is at these spots and then what's actually happening at the function. And what we kind of got the sense of is that if the slope of our line is positive, right, if we're pointing up, right, the slope of our line is going up, but the function is increasing from left to right, that we're moving in that direction. And that's kind of what I envision, is I can just kind of see myself like pointing in that direction. Like, okay, I'm looking out, or I'm looking up, or I'm looking down. That's kind of the direction that I'm going to be moving in when I do that, right? And so when things are pointing down, depending on how steep they are, right, those tangent lines are only going to exist when the function is decreasing, when they're pointing down like that. And if we are at a relative minimum or a relative maximum, we definitely need a horizontal tangent line at those spots. Now, it doesn't have to be at a minimum to have a horizontal tangent line, but if we are at a min or a max, it definitely has one, right? Because we could draw something that looks like that, right? And right here, sure, there is a horizontal tangent line right at that one spot right there. But we go from increasing to flat to increasing again. And seeing slopes of lines that are positive, then zero, and then positive again. Not seeing that sign change on either side bothers us about trying to find a local extrema if we've got one. We want to see it go positive, zero, negative, or negative, zero, positive if we want to see that change. And so we can kind of like do some investigating, not just at the spots where the derivative is zero, but on either side as well, and get a sense for what the function's doing in those spaces. And so if we see that sign change, right, positive, zero, negative, or negative, zero, positive, or positive, zero, negative, that's a minus. It gives us kind of a sense of what's happening. And that sign change is really, really valuable to us. But early on, we just kind of said, all right, you know what? And hopefully you wrote this down on the top of page 124. If the derivative is positive, then we're increasing, right? I think we did kind of like an if-then kind of setup, that we looked at kind of three scenarios for what might be happening, right? If the derivative is positive, if the derivative, and you should have this from yesterday, if the derivative is negative, or if we are actually zero. And we were pretty confident saying, like, guaranteed, then the function itself is definitely increasing. The function itself is definitely decreasing, and there's nothing kind of sway me from that. I feel really, really confident that if those things are true, it's either going up or it's going down. But if the derivative is zero, there might be an extremum, but maybe not, right? Maybe not, right? So there may be an extremum, but we don't know. but there could be. Maybe there's an extremum there, maybe not, right? What we wanted to see, if we wanted this to be true, is we needed to see a sign change of f prime of x. I wanted to see the derivative change signs kind of on either side of whatever those x values are. And so, if I see that I think x equals 3 could be an extrema because the derivative is 0 there, well, let me see what's happening at 2 and at 4 and kind of compare on either side. And that's a really great way to kind of get a sense for finding that turning point, which is something we couldn't do without calculus up until this point. So that's really nice. If we see a sign change, great. And if we don't, great. That's okay too. It's just not going to be a min or a max. It's just going to be that flexing point where we kind of take that second just to flatten out, but we kind of continue off in the direction that we're going. And once we have that, right? Once we have this idea that, okay, I can stop at a certain spot and figure out what's happening in the graph. Well, now I can look at an entire graph. And this is kind of where we started to end up, not quite all the way there yet. This is the top of page 125. Don't get this confused with a graph that looks kind of similar. Now we can look at entire intervals where the graph is increasing, where the graph is decreasing, or where the graph could have a horizontal tangent line. Because when we see things like this, all right, top of page 125, if g prime of x is negative, right, less than 0, in my mind, what I really think about, not about the derivative, but about the function. Right, the g of x is decreasing. From left to right, I'm just kind of heading down. I'm on the down slope somewhere. I'm here, or I'm here. Right, all of those sections, because we're looking at the function, right, the graph that we have is g of x, then I can make some kind of leaps to what is happening with g prime of x. Oh yeah, between -4 and -2, x value intervals, right? And then from 1 to infinity. That's all good, I like this, right? Same thing where the function's increasing. That's going to happen where my derivative is positive. Like all this space over here and all this space over here. Right, so something like -infinity to -4, and of course I can't include those endpoints. So -2 to 1, because those endpoints are where the functions actually, I'll go to a different color here, where we actually have that horizontal tangent line at those 2 spots. And so when I think about the derivative being equal to 0, I don't necessarily say, oh, that's going to be a min or that's going to be a max necessarily. What I have in the back of my mind is a horizontal tangent line. That's kind of my first thought. Is let me start first by finding those spots where the function flattens out ever so briefly, just for that moment in time at places like, and so these are actual x values, right? I'll write it as a set. I don't have to use the set notation. At those 3 spots, right? When that x is -4, when it's 2, and when it's -2. And sure, they also happen to be relative extrema, and that's really nice. And it's because you can see the side change, right? It goes from blue to red or red. Cool. That was kind of the gist of everything. We talked very, very, very briefly about the normal line. And I'm leaving it brief on purpose. When we talk about the normal line, it's just perpendicular to that tangent line. We're just going to put a pin in that and kind of keep that in the back of our minds. It's really just a connection between the tangent line and something else, so I draw the tangent line at -3 right there. Okay, cool. The normal line has that right angle. That's all the normal line is. It's just perpendicular to the tangent line at the point of tangents, right at that exact spot. So they share the same point. Their slopes are just negative reciprocals. Does that help kind of solidify yesterday's stuff? Any other lingering questions about connections between the function and the derivative? Kind of in both directions, we want to be comfortable. And that's kind of what happened when we got to this page, page 126. Let's start here right now and really kind of get into it. The thing that's a lot harder about this than it looks is because they didn't give us the graph of the function, they gave us the graph of the derivative. Yeah. Cool. Right, and that's what I want to do. I want to try to like kind of break this picture down and be like, how am I supposed to figure out what the function looks like if I'm looking at the derivative, and vice versa. And so what I think is important for us to kind of keep in mind are, obviously it's a race, but like what we've created in that space right there, that if this is true, then that is true kind of scenario. Now we just go in the other direction and we say, okay, look at the three sections in that table. If the derivative is positive, the derivative is negative, and if the derivative is actually zero. And so if I'm looking at the derivative, really what I'm going to do is I'm going to break this graph into those three sections. The spot where this graph is positive, where this graph is negative, and where this graph is zero. Not where it's increasing, not where it's decreasing, and not where it has a horizontal tangent line. That's the function. I'm looking at the derivative. And so it kind of gets broken up this way, like these spots right here is where the derivative is zero. And so what that kind of creates in my mind when I see that is I say, oh, those spots must be the places where h of x has a horizontal tangent. Right? At -2 and at 1 and at 3, those are the spots where I can draw that perfectly flat line that maybe it's a min, maybe it's a match, maybe it's just that kind of that turning point where it flattens out so ever so briefly. And so what that does, it kind of breaks this graph into like this whole top section up here, all of this, like all of this up here, and all of that up there, that whole space, that is where the derivative is possible. And so if that's where the derivative is greater than zero, tell me what's happening at the function, at every single one of those values that I just kind of colored over in blue. What's increasing? The function itself, h of x, is increasing. And all I think about in my mind when I say increasing is it's going up from left to right. And if I was walking along that path, I would be looking up while I did it. Right? I'm rolling the ball up the hill. Question?
What about from -1 to 1? Is that not decreasing?
The derivative is decreasing. Absolutely. But the function, when the derivative is positive, and here's the tricky part, when we look at points, we're not looking at like x f of x, or in this case, x h of x. This point is x comma h prime of x. The point -1, 5, the point that we're looking at on this graph, says that, hey, if you go to the function and you stop at -1, it's not that the point is at 5. The slope of the tangent line is 5 at that point. And so it's relating points on the graph not to their like values, but to their derivatives, the slopes of the tangent lines as we kind of move along. So what I have there with that whole kind of blue section above is I have the entire section of the graph where the function's increasing. And don't worry, we're actually going to try to draw the function here in a second. Like if this is the graph of this, what does the function itself actually look like? But we don't want to forget, like we have this whole entire section down here where the derivative is negative. And so what's happening in that section for the function if I know that the derivative is negative in all those places? What are the characteristics of the function? If I was looking at the function, what would it be doing in those areas? It'd be decreasing. H of x is decreasing. And we can kind of break down those intervals where that's happening. Like, okay, the function that's where is it increasing? Oh, between -2 and 1 and from 3 to infinity, right? Where is it decreasing from -infinity to -2 and from 1 to 3? And we have these sections where I can say, oh, I know what this graph is doing. Now, I don't know where it's doing it. Like, I don't really know like how far up and down the function is. I don't really know a ton about its location, but I know about kind of the behavior of the function along the way. And so what I've got, though, which is really nice, is we have some sign changes around all of those spots that we have horizontal tangent lines, right? We go from decreasing to 0 to increasing. And we're increasing this whole way. And there's a point right up here where it is increasing the most. Because remember, that 5, that value right there is the slope of the tangent line. And at every other point, we're at 4 or 3 or 2 or 1, slope of the tangent lines are less than that. When we get to a spot like -1,5 on the derivative, and we see that, what we're looking at is a place on the function where the slope is the steepest. It's 5 at that spot. Whereas on either side, maybe it was just 4 or 3 or 2 or 1, and eventually it gets down to being 0. And so as much as I kind of want to fill in all this stuff, what I think might be more useful is trying to draw out what this function might look like. Now, if you drew what I just did, then you might have covered up this space over here. And so I don't care where you decide you want to draw it, because we're not going to fill in these intervals because we just kind of drew those right there. I want you to find a space on this page so we can kind of look back and forth. And we're going to try to sketch out this graph. Now, I'm going to do it right here, just because it's going to be easy for me to have the two next to each other. But if you drew this, and I thought writing this stuff down would be very helpful. Find any other empty space, in the boxes below, whatever you want. But I'm going to draw it right over here. Actually, you know what I'm going to do? I'm going to draw it over here because I want to keep the increasing, decreasing stuff. Okay, so find a space. Let's draw a set of axes that is as identical to those as we possibly can. And I'm going to mark off the -4, -3, -2. I'm going to go -1, 2, 3, 4, and 1, 2, 3, 4. Okay. This is going to be the graph, at least like a possible graph for what h of x might look like. And again, we don't know exactly. If we don't know anything about the function itself, we just know the derivative, we can just kind of sketch it as best we can. And all I know is that in this green section here, kind of from -infinity to -2, so all of this kind of leading up to here, all I know is that the function is going down from left to right. That's all I know. But I don't know where. I don't know if it's going like from here to here, or there to there, or there to there, or something like that. But what I know for sure is that the function is going down until I get to -2. And so let's draw that. But I'm not going to put -2 on the x-axis necessarily. It doesn't have to be an x-intercept. Maybe we say, hey, at -2, there's a point like over here. So go ahead, give yourself a point like at -2, comma, whatever. We'll put in like the negative space. Doesn't matter where it is, but that just gives us some space to turn. And all I really know is that the function is decreasing as we go down to it. But that spot right there is a location where it has a horizontal tangent line, guaranteed. In fact, I'm even going to approach that even a little softer. Because like as soon as I get to there, there's a horizontal tangent line. But what is the function supposed to do after that point at -2? What's the behavior of that function as soon as I get to -2 and beyond? it's got to go up again. How do I know that? Because the derivative is positive. And there's going to be a point at -1 where it will be increasing the fastest, right? You can almost kind of think of h prime of x, the derivative of a function, as the function's velocity. How fast it's changing. It's its rate of change. Because it's the slope of the tangent line. If I roll a ball down the hill, if I find that steepest point, it's going to be rolling the fastest. But I have to take a turn, and I got to get myself increasing. But there is a spot where that increasing is going to stop. And that's right here again. That somewhere at +1, this function is going to stop going up, and it's going to have horizontal tangent lines somewhere. So I'm just going to give myself a target. So I'm going to go to 1 and like up here somewhere, wherever. Now, it doesn't matter. It could be there or there or there or there or there. I just have to give myself enough space to do this. From -2 to 1, this function is going up. How do I know that? Because the derivative is. But then from 1 to 3, I got to go down again because my derivative was negative. Now, I don't know exactly where it's going to be. Hey, maybe it happens here. Why not? It could be an x-intercept. That might just be lucky on our part. Doesn't have to be, though. It could be anywhere. I could have put that point here, 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 anywhere on that spot for 3, as long as I give myself the space to decrease on the way. Okay, but then after that, here I am going positive again. I have to increase and head up. Okay, and that's just our best estimate. We're probably not super accurate in terms of, all right, is the slope of the tangent line actually 5 at -1, or is, or is it a little flatter than that? Okay, I didn't do a great job at actually making that my steepest point. But if we get kind of a sense of like decreasing, 0, increasing, and we get a sense for like how to draw that, okay, then at least we're kind of making those connections. And that's the big part, trying to connect what I know about a function, what I know about the derivative, and kind of working in both directions. Cool. Okay, and we will definitely kind of work through that. It's a skill that comes with time more than anything. It's just going to take some practice. Okay, so I'm moving along here though. Let's turn to 127, and I want to look at that graph there in the middle. Any questions about that conversation? No, does that sit okay with you? Okay. Slow me down if you need me to, of course, as always. I want to help, so just give me a shout. Move you guys a little closer. I wonder if that would help. Okay. All right, so we're not going to do number 1 on this page. I want to just look at 2 through 6, okay? And now, again, we have to look closely at what they've given us, because if they give us the function versus the derivative, we're looking at 2 totally different kind of mindsets. All right, now they're back to just giving us the function. And all we're going to try to do here is kind of go through 2 through 6, labeling some points, A, B, C, D, E, and F. And seeing if we understand that if they want me, number 2, to label some point A, so I'm just going to put a point, and then I'll put a kind of a big capital A next to it. I want to find any spot on this graph where the derivative is negative. So what do you think? If we are looking for a spot on this graph where the derivative is negative, what are we looking for on the function itself? So, between here and here, and after that, why? That's it. It's going down. Perfect way to say that. So pick any spot you want. I don't know, right there. Lovely. There's an A. I feel really good about that because they're asking me for the spot where the derivative is negative, so all I'm looking for is a spot where it's decreasing. Now, that, like Sen said, any point in this section or in this section would be good. Okay, so that is where the derivative is negative. Okay, now they want a spot where just the value of the function is negative. Nothing about the derivative. Don't overthink it. Pick an x value for me, and I'll plot a point on the function there where you think the value of the function is negative. 6.5. Perfect. There it is. Right about there. I'm just below the x-axis, right? So I still kind of need to have that little background. I don't want to lose that. Okay. Now we start to have to look a little bit closer. Because there are a lot of answers for A and a lot of answers for B for sure. But when we get to C, now it says, okay, find a spot on this graph where the value of the derivative is as big as possible. Okay? So when I think about big numbers, I'm talking about like numbers to the right on the number line. Big, big, big numbers. 2 is bigger than 1. 3 is bigger than 2. 5 is bigger than 4. -2 is bigger than -3. Okay, so numbers to the right, yeah, on the number line. And so if we're looking for a spot where the value of the derivative is really big, think hopefully positive numbers if we can, of course, right? What are we kind of looking for in terms of the value of the function? Yeah. To the left of, like, what do you mean? Like just to the left or? So like really close, like right there, or like a little further down here or down here? Like, what do you? So we want to be increasing for sure, because that'll give us a positive number, okay? And so, and I'll just give us a couple of options, like right there, or right there, or right there, maybe like right there, or right there. We want the derivative to be really big. Yeah, go ahead, Jess. Okay, so increasing the most, nice, because the derivative is really, really big. And so what are we kind of looking for in terms of the line itself, maybe the tangent line at that spot? Increasing the most. So what is that? I love that. That's perfect. Like kind of going up the fastest, right? Trying to find a spot where whatever tangent line we would draw would be super, super steep. If my function is going up really, really fast, the slope of my tangent line at that spot is super, super steep, pointing almost vertically if I can. And so these points, like as we start to get closer and closer to a maximum, you're going to see that those tangent lines start to flatten out, right? They're going to like round themselves out and start to get flatter. And so we might be at like 1, but then 1/2, 1/3, 1/4, 1/5, right? We're going to get smaller and smaller. And so we're looking for points usually like pretty far away from a maximum or a minimum, certainly in this point, from that maximum, so that we get that steepness. I want to find any point on here that I feel like you said, the function is increasing the fastest. I don't know, like the beginning maybe? Or what do you think? Tangent line, 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 tangent line. I feel like the closer we get to that maximum, the flatter it starts to get. And so I think in this case, the further we go here, I feel kind of good about saying, you know, like even like, well, it's not kind of tough to tell, but almost even like right there. We don't want to really get close to a maximum or a minimum if we want our slopes to be super steep. Because what you're going to see with these continuous and even more importantly, these rounded, smooth, kind of soft functions, like these rolling hills, if you will, is that the closer you get to a maximum and minimum, those tangent lines are going to start flattening out. They got to start like getting softer and softer and slower and slower and slower. I don't want to be decreasing or increasing very quickly as I get there, so I can have that rounded edge. Now a graph like this is going to be a very different story, right? Those are just two lines that meet there, right? When we talk about absolute value, it's really a piecewise function of two lines. The slope of this line does not change. The slope of that line does not change. If this is literally the absolute value of x, the slope of that line is -1. The slope of that line is 1, always. Until magically it gets to here. And so we don't see that kind of gradual turn and change, and that's not good. I want to see this action, right? As I approach, let's say that minimum right there. Okay, steep, not as steep, not as steep, flatter and flatter and flatter. Oh, 0. Now I can start increasing again. It's going to have this kind of gentle turn to it. Whereas these sharp turns, don't like it. As nice as it is to be continuous, we also want that smooth and rounded nature. Okay, a couple more. Label any point on this graph where the derivative is 0. Go ahead. Call that point D. Find any spot where you think the derivative is 0. How many options do we have? Yeah, 3 of them, for sure. This one, that one, or hey, I'll pick this one. That one right there. Anybody else pick that one? Nice, cool. But any of those 3 would all be good. I like it. 6 is kind of funky. Label 2 different points, E and F, where the values of the derivatives are opposites of each other. What does opposite mean for us? Positive and negative, different signs, but like are -3 and 5 opposites? No. What's the opposite of -3? Huh? Not the reciprocal. So I'm not looking necessarily for negative reciprocals. We're not looking for perpendicular slopes. We want just opposite slopes. So it's opposite signs, but the same absolute value. So 3 and -3, 5 and -5. The easiest one, I think, in my mind, to find opposites, probably be 1 and -1. Okay? Trying to find a spot on this graph where the slope is 1 and where the slope is -1. And it's kind of hard to tell because we don't really have any grid lines, but and the tick marks aren't necessarily perfectly evenly spaced. But you can kind of do the best you can and say, I don't know, like I was gonna like really kind of slant my tangent line so it was diagonal, like perfectly diagonal this way. That would be a slope of 1. That would be a slope of -1. I don't know, like maybe right there. That kind of looks like a slope of 1. Let me call that E. Where do you think we could put F? A slope that might be just the opposite of that.
Right before the first,
Like here? Right there? That looks pretty good, right? It's not super steep. I think that's a great spot for an F. Is there another spot maybe where you would, oh, no, that's already positive one enough. We don't want to go up again. We want to go down. So maybe just after that peak, maybe right there. That might be a good spot for an F. Any other spots where you think might be a good spot for like a -1 kind of slope? Just after point D, kind of like maybe like right there. Yeah. Any other points? Maybe just like on the other side over here too. I feel like any of those, and I'm just gonna put one of them. Anywhere, I think will be pretty. And that balance kind of on either side of a min or a max is kind of a nice place to look for that. Okay? If you have that nice kind of curvature, nice and round, some balance on either side, you might find some opposites. And so if I'm looking for the opposite slope for something like A, I might just go like straight across onto the other side. Opposite slope for something like C, maybe just kind of straight across it and looking almost at like point B for that one. Cool. Just kind of getting you estimated. All right. Yay. Guess what's coming? All right, we're going to skip this. Here's a good one. I'm going to save this for you for another time, but this is going to be good practice as you get a little bit better at it. 4 functions, 4 derivatives, and you have to match a function to its derivative. But today's the day. Turn the page. Let's go to page 130. Okay, we'll work our way back. But I wanted to get this to you now so we can start to get a little bit better. Okay, so starting at the top there, some function. This kind of made one up for us. F of x equals just 3, right? Just y equals 3, just going kind of straight across. Right, what does the graph of this function look like? Well, I don't know, I'll just draw myself a little sketch or something. Here's the function f of x equals 3. There's f of x right there. What's the slope of that line always? 0, right? So in the case of this function right here, the derivative is just going to be 0. And I think you probably feel pretty good that if that function is any constant, doesn't matter what c is, but if we're looking at a function that's any constant, right, then the derivative of that function, no matter what, will just always be 0. Okay? And so kind of that first initial takeaway is that the slope of a constant, the derivative of a constant is 0. Okay? The slope of a line is just the slope of the line. So the derivative of a line is just going to be its slope. Okay? Now, what I'm going to do with these here, I'm going to scoot myself back just a little bit so I can see all of them at once. There we go. I am going to write down the derivatives. I want to see if you can figure out how I'm doing it. Okay? So I'm going to start every single one of these. They're all f of x. So all of these are all going to be f prime. So you can start writing that if you want. F prime, F prime, F prime, all the way down. And what I will do is write down the derivative. See if you can figure out what I keep doing over and over and over again. Okay, the first one, the derivative, is 6x minus 2. Guaranteed. Now, to help you out, I'm going to do this. Plus 0. Now, of course, when we write the derivative, I'm never going to write it plus 0, but for good measure, so you can see it, there it is. Okay, next derivative, negative 15x squared plus 4x minus 3 plus 0. Zero minus 9x squared plus 24x. Two x to the negative second power minus 6x to the negative. Four x to the negative 1/3 minus 8x to the negative. And last one. 3x to the negative 3/2 plus 3/2 x to the negative. Now, before we get into the algorithm, about maybe what's happening as I'm working through those as quickly as I was able to, let's talk first about these setups. What do you notice about all of the functions as they're written right now? Yeah. Before you get to the algorithm, before you get to how I found the derivative, let's talk about the setups for each of the functions before we talk about what I'm doing with the number. Before we talk about the derivative. I know, you get it, I like it, I'm happy. Let's talk about this. What do all of these look like? Functions, yay, good. And as like obvious as that might like yeah, they're all f of x. This doesn't work if they're not functions. Okay. Now they can call it y equals for sure, right? It doesn't have to be f of x, and of course we can call it g of x, h of x, whatever. We have to have functions. Okay. Now get a little more specific. What kinds of functions are we looking at? On their domain, yes. All of the functions are continuous on their domain, but not all their domains are infinite. But yes, on their domains, they are continuous, and that's crucial for us, for sure. The only ones that I'm worried about are things like the 1/2 and the -1/2. So we got square roots. You just have to watch what numbers we plug in. But if I can plug a number in, I'm going to get a y value back. We won't have holes or asymptotes or anything like that. Hopefully, fingers crossed. But if we do have an asymptote, it's still continuous on its domain. It's just missing some values, so that's okay. Thank you. These are polynomial functions. Now, they all have that polynomial kind of setup, right? Now, the reality is that some of these are rational, right? That's -2 over x. That's +3 over x squared. That's a rational function. There's a radical function. There's a cube root squared. They're not necessarily polynomials in the sense that all of their exponents are integers, but they're all written in what's called polynomial form. And that is super crucial. If it's not written like this, I can't do what I just did. Okay, what did I do? What do you mean I took away an x? What does that mean? So the exponent, so what you're saying, so like that exponent of 2, where does it go? So it decreases from a 2 to a 1, okay? And then, but where did the 2 go? Yeah, yeah, I decreased the exponent by 1 to get it from a 2 to a 1. But what happened to the constant in front? Okay, so it's kind of like that exponent gets dropped in front, gets multiplied through by whatever constants are there, and then the exponent decreases. Like it just kind of goes away. Like the 2 doesn't become a 2 anymore, and now it's just gone. Okay, let's expand on that. Megan, what do you see?
That you multiplied for the first one, like 3 times it.
Okay. Yeah.
And then the -2x has a 1 as an exponent.
So this is a 1 right here, okay.
Yeah, so you multiply that and then 3.
And so that still works, right? You're still multiplying your exponent by your constant, but it just doesn't change for that one. But where did the x go then? Why? Do you think? Well, let's talk about like what is that exponent for x right here if it makes it disappear? It's x to the 0. Okay. Good. So let's keep going. Do things kind of continue in that same fashion? And what is that fashion that we're really looking at? Because we want to get more focused in on a really, really solid algorithm that works all the way through. What are we seeing all the way through? Well, what happens with the constants at the end? What happened to all of those? The 3, the 1, even the 6 in the front of the third one becomes 0. So we're going from a function to a derivative, right? The derivative of a constant is 0. So it's almost like when I get to like this 3, I just say, oh, the derivative of that is just 0, right? The derivative of 1, just that like that little part, oh, okay, that's just 0. The derivative of that 6 right there, like I just kind of focus in on that one. Oh, okay, the derivative of a constant is 0, and now I'm ready to move on. Yeah. So when I look at, and you're kind of looking like one term at a time, right? We're not looking at the whole function all at once. I'm just kind of saying, all right, I'm going to focus on the 3x squared, see what happens. I'll focus on the negative 2x, I'll see what happens. I'll focus on the 3 and kind of see what happens. And every time we go from a function to a derivative, every term does what? What happens to the degree? It goes down 1, right? 2 became 1. 1 became 0. Now, the derivative of a constant is just 0, so it's not like I'm going from x to the 0 to x to the negative 1. The derivative of a constant is 0. But look, 3, 2, 1, 2, 1, 0. 3 and 4, 2 and 3. Negative 1, negative 2, even those go down 1 each. Absolutely. Okay, good. So it looks like there's some connection between the exponent decreasing by 1, but that exponent doesn't just like disappear. Does his idea of taking this 2, multiplying it through the 3, like Megan's idea of saying, okay, like the 1 times the negative 2 is still negative 2. Does that happen all the way through? Is every original exponent getting multiplied through the constant in front of that term, and then we decrease the exponent by 1? Like, look at that term right there, negative 5x cubed. Does that hold true for the value of the derivative for that one? 3 times negative 5x, and then I just decrease the exponent by 1. Even here, right? Negative 2x and the negative first. Okay, negative 2 times negative 1, ooh, positive 2. And then decrease the exponent by 1. 6x to the 2/3. Yeah, 6 times 2/3 is 4. 2/3 of 6, all right? And then decrease the exponent by 1. 2/3 minus 1 is negative 1. That's the shortcut. That is what's known as the power rule. Oh, look at that timing. Money. Now, tomorrow, we're going to talk about a new notation for derivatives. Okay? But now that we've got that shortcut, now we can use it anytime we want. Okay? Limits, besides when we take a test, no more. Now we've got a shortcut and we can use it every single time. Okay? We'll talk about what that notation looks like tomorrow. Thanks, everybody. Thanks. Awesome. Thank you, guys. See you. Later.